All right, I hope you enjoy the break. All right, so we covered 4-1, 4-2. Today we are going to cover complement and conditional probability and Bayes' theorem. Hopefully we'll go cover also counting and probability through stimulation. We'll see. So the focus on this topic is how we get probability of at least one of some specific event. Okay, what is the chance of getting at least one boy in three birds? What is the chance of getting at least one girl in three birds? Right? At least one. We also will focus on conditional probability. So the probability of an event occurring when we have additional information that some other event has already occurred, right? So the chance of getting something by considering that something else has occurred, something else has happened, right? And also we talk about Bayes' theorem. Now, the probability of at least one. When finding the probability of some event occurring at least once, we should understand the following. At least one, at least one has the same meaning as one or more. So when you say at least one, it could be one, it could be two, it could be three, or more. So but the minimum is one. Now, remember the complement of getting at least one, right? The complement, like the opposite of getting at least one. So that would be none, no occurrences of that event. So let's say chance of getting at least one boy. So that means no boys will be the complement in this case. Excuse me. Now, how do we find the probability of at least one of some event? First, we start off getting at least one of some event. So that's, let's say we name event A as getting at least one of some event. That's the name of event A. Now, then event A bar could be getting none of the event being considered. So as I mentioned, if you say A is getting at least one boy, now A bar will be getting getting no boy. All children will be girls, for instance, right? So that will be the complement of A. Remember, A is getting at least one boy. So A bar will be all boy. All children are boy, right? Now, remember, P of A is probability that even A occur. Now, P of A bar will be probability that even A does not occur, because A bar is a complement of A. Now, to find P of at least one occurrence of even A, so which means to find P of A, we do 1 minus P of A bar. Remember, P of A bar is a complement of A. So what we have here, probability that even A does not occur. So 4, we subtract the result from 1. So because we know P of A plus P of A bar is equal to 1. So you just do a one basic equation, solving equation, by doing P of A is equal to 1 minus P of A bar. It's very easy. Now, let's take a look at this example. A study by Square Trade found that 6% of damaged iPad were damaged by bags, such backpacks or backpacks. If 20 damages iPad are randomly selected, find the probability of getting at least one that was damaged in a bag or backpack. Is the probability high enough so that we can be reasonably sure of getting at least one iPad damaged in a bag or backpack? Right? So there are two things we need to do here. First, we need to find the probability of getting at least one iPad that was damaged in a backpack or in a bag or a backpack. At least one. So that means from 1 and up. Then the question is this high enough so we can be sure that at least one iPad damage in a backpack was damaged in the backpack based on the value of the problem. Now let's see. We name event A. Let at least one of the 20 damages iPad was damaged in a bag or backpack. At least one of them. So what should be A bar then? Remember, A bar is the complement of A. So at least one, so we have to say A bar must be none of the iPad was damaged in a backpack. So that means we identify A bar, which is a complement, not getting at least one iPad damaged in a backpack among the 20 iPad. So this means all 20 iPad damaged in a way other than bag or backpack. They were damaged, but not in the bag or backpack, but different other ways. So now step 3, we need to find the probability of the complement of evaluating P of A. P of A bar, which is complement A, which P of all 20 iPads damaged in a way other than bag or backpack. Right. So remember, P of an iPad damage in a backpack is 6%. It's given, right? iPad damage in a bag or backpack is 6%. That's given to us. So which means if 20 iPad damage in a way other than the backpack will be 1 minus 0.6. 0.06, which is 0.94. So that means the probability of getting all 20 iPad damaged in a way other than the back will be 0.94 times 0.94 times 0.94, 20 times, because we have 20 iPad. So that means probability of iPad 1 damaged in a way other than bag or backpack, time probability of iPad 2 time probability iPad 3 up to probability iPad 20. So each one, P of the first iPad will be 0.94, the second iPad will be 0.94, and so on. Remember, this is a multiplication rule. We have to multiply the probabilities. So when you multiply 0.94 by 0.94 by 20 times, that's just 0.94 to the 28th power. If you can use a calculator to figure out this, and you get 0.290. Remember, 3 significant digits rule. So now we just need to find P of A. This is P of A bar. This is the chance of getting iPad damaged in other way than bag or backpack. So all we have to do now is to subtract this from 1. So we find P of A by evaluating 1 minus P of A bar, which is 1 minus 0.290, which is 0.710. So that's the probability of getting at least one iPad that was damaged in a bag or backpack, 0.710, which is much higher than the other one. So for a group of 20 damaged iPad, there is a 0.710 probability of getting at least one iPad damaged in a bag or backpack. So we can say about 71% chance of getting at least one iPad damaged in a bag or backpack. So it's much higher than 50. So the question was, is this probability high enough? So the answer is this probability is not very high. So to be reasonably sure of getting at least one iPad damage in a backpack, more than 20 damaged iPads should be used. So more than 20, because the number is still low to be sure. So it's not high enough. Okay. Now the next thing is conditional probability. Conditional probability of an event is a probability obtained by the additional information that some other event has already occurred. So this means we're dealing with two different events. There are one is the occurrence of one event will affect the occurrence of the other events. Why we call it conditional probability notation. So P of B in respect to A. So which means the probability of B occurring given that event A has already occurred. So we are determining the probability of B occurring, but by keeping in mind A has already occurred. So we call it conditional probability. It's based on so we say the conditional probability of B occurring given that A has occurred can be found by assuming that event A has occurred and then calculating the probability that event B will occur. So we already know event A has occurred. So now we are determining the probability of event B, right? B occurring. So this is the formula. P of B with respect to A is equal to P of A and B, probability of A and B occurring both, divided by probability of A. Right. So again, P of A with respect to A, P of B with respect to A is equal to P of A and B divided by P of A. Remember we said about P of A and B. It's a multiplication. So P of A and B, if they're independent, so just P of A times P of B, right? We covered 4-2, I believe. Now, let's take a look at this example. Pre-employment drug screening. Find the following using the table. So we have the table is given. We have to determine the probability. If one of the 555 test subject is randomly selected, so we have 555 here. If you add all the test results, you add up to become 555. That's where it's come from. So the question is, find the probability that subjects had a positive test result given that the subject actually uses drug. So this means find positive test result with respect to subject uses drug. So you can, in this column, it says subject uses drug, 45 true positive. So when you say true positive, that means those subjects are actually tested positive. It's for real. So when we say false positive, that means these people are tested positive for, but it's not real. So that's why we call it false positive. Right? So we can see here negative test results. So we have 5 false negative and 480 true negative. 5 false negative. That means these people actually have a should be test positive, but it's a false negative. They are not negative, but it's a false negative. It's not true negative. We have 480 true negative. So the question is to find P of subject uses drug with respect to positive test result, right? So we have to use this approach called intuitive approach. We want P of positive test result with respect to subject using drugs. If we assume that the selected subject actually uses drug, we are dealing only with the 50 subject in the first row. So remember, there are 50 subjects in the first row, subject to use the drug. So 50, the total number of subjects there, 50 in the first row. Among those 50, 45 had a positive test result. So we get this result, P of positive test result with respect to subject use the drug would be 45 out of 50, right? 45 because there are 45 positive test result. So because it's a positive test result with respect to subject to usage drug. So when you divide 45 by 50, you get 0.900. But we have to use follow this 3 significant digit. That's why we added 2 zeros behind the 9. Now, formal approach. The same result can be found by using the formula for P of B with respect to A, given with the formal approach. So again, P of B with respect to A is P of positive test result with respect to subject to usage drug, or B is a positive test result and A is subject to usage drug, right? So A is subject to usage drug and B is a positive test result. So we have two events here. Go back here. So you get this form P of A slash A, P of B slash A is equal to P of A and B divided by P of A. Okay, so we have here P of subject uses drug and how the positive test result is 45 over 555, right? And P of subject uses drug is 50 over 555, right? So this is a multiplication rule here. We use a multiplication rule, but by looking at the table, you can just determine the number. P of subject uses drug and has a positive test result. So the total will be 45 out of 555. Then the bottom one, subject uses drug. So actually 50 because when you consider the false negative one. Okay, so divide this to. So when we compare the intuitive approach and the formal approach, it should be clear that the intuitive approach is much easier to use, right? So that's much easier to use. And it also less likely the result, you make less error when you use it. But you are free to use either one as long as you follow the right step. So here we want P of subject to use drug with respect to positive test result. This is a property that the selected subject uses drug, given that the subject had a positive test result. If we assume that the subject had a positive test result, we are dealing with the 70 subject in the first column, right? Because there are 45 and 20, I believe 25, so that's 70, right? If we assume that the subject had a positive test result, we are dealing with 70 subjects in the first column. We go back to the table. So among those 70, 45 use the drug. So 45 out of 70, which is 0.643. So subject to use the drug slash positive test result, right? So with respect to positive test result. So the first positive test, the first result of P positive test result slash subject to use drug equals 0.90, indicate that the subject who uses drug has 0.90 probability of getting a positive test result, right? Subject who uses drug have 0.90, much higher chance of getting a positive test result, right? So the second result of P of subject to use drug versus positive test result is 0.643, indicate that for a subject who gets a positive test result, there is 0.643 probability that this subject actually uses drug. About 64% chance that this subject actually uses drug. Okay, so this is just an interpretation. Okay. Now you can see here P of positive test result with respect to subjects to use the drug is different than P of subjects to use the drug with respect to positive test result, right? So subjects to use the drug and positive test result, they are different. And you see when you switch the order, it's like you switch the order, they are not the same. In other words, P of B with respect to A is different than A with respect to B. P of B with respect to A is different than P of A with respect to B. So they are different, right? So keep that in mind. So they look the same, but they are different. So to incorrectly think that P of A B slash A and P of A slash B are equal, or to incorrectly use one value in place of the other is called confusion of the inverse. So we cannot do that. So for instance, if you say D, we have these two events. D, it is dark outdoor. M, it is midnight. All right, could be midnight. It could be dark outdoor, but do they mean the same? P, P, D slash M. So that's one. It's dark and midnight. So that means it is certain to be dark given that it is midnight. For sure, if it's midnight, we can say it's dark outside, unless light is on everywhere. But if it's midnight outside, there's no light, it's dark because there is no sunlight. Now P of M with respect to D. So the probability that it's exactly midnight given that it is dark outside is almost zero. So the probability that the chance that it's exactly midnight. So it can be dark outside, but that doesn't necessarily mean it's midnight. It could be dark outside is 1 a.m. or 6 a.m. or 4 a.m. But it doesn't necessarily mean it's midnight. So the chance is zero, right? So you can see here, these two are different. 1 and 0 are not the same. So you can see P of D slash M is different than P of M slash D. The bias theorem. We extended this discussion of conditional probability to include application of bias theorem, the rule, which used for revising probability value based on additional information that is later obtained. So let's say we want to interpret medical test result. Assume cancer has 1% prevalence rate, meaning that 1% of the population has cancer. So let's see the chance of even of having cancer by, right? Having cancer. So P of C is equal to 0.01. The chance of having cancer, because the prevalence is 1%. So for a subject randomly selected from the population, so you can see false positive rate 10%, true positive rate 80%. So 80% out of this number, positive test result. So this is true. 8 out of 10, right? When you see here, 80% of that would be 8. Right? When you have 10 subjects, it will be the 80%. All right. So assume that we have 1,000 subjects with 1% prevalence rate. 10 of the subjects are expected to have cancer. So that's why we have false negative. That means these two are also have cancer because there is false negative. There's no true negative. The sum of the entry of the first row of value is therefore 10. So you have 10 here. Right? 10 of the subjects are expected to have cancer. Next one, there are 999 subjects do not, the other 990 subjects do not have cancer. So there must be false positive and true negative. So when we say false positive, they don't have cancer, but that's what we call false positive. And this one is true negative. They don't actually have cancer. Based on they have a negative test result for real. These people have positive test result for fake, not real. So when you add this, it's 999. So this other 999 subjects do not have cancer. So false positive, they don't have cancer. True negative, they don't have cancer. So that's 990. Okay. So among the 990 subjects without cancer, 10% get positive test result. So 10% of the 999 cancer-free subjects in the second row get positive test result. So they enter 99 in the second row. So that's why we have 99 here. So 10% of the 990 cancer-free subject. So 10%. So when you take 10% of 990, you get 99. So that's why we get this. That's positive. So we can read this here too, because the total is 990. So we take away 99 from 990, you get 891, right? So that's and we talk about this again, but let's read. Among the 10 subjects with cancer in the first row, 80% of the test results are positive. So 80% of the tests of the 10 subjects in the first row test positive. So 80% of 10, when you calculate 80% of 10, you get 8, right? Okay, good. So the other two subjects in the first row test negative. So the entry of 2 in the first row, right? So 2 negative. 0.48 from here, when you turn this to a percent, you move this 1.2 spaces to the right between 7 and 4, so you get 7.48. So for randomly selected subject given a test with a positive test result, positive result, the chance of cancer increases to 7.48. Based on the data given in this example, a positive test result should not be devastating news because there is still a good chance that the test is wrong. Yes, that is true. Because we have false positive, we have true negative. So we have the last two slides are this prior and posterior probability. The prior probability is just an initial probability value ordinarily obtained from before any additional information is obtained, right? So that's given to you. And now the posterior probability will be is a probability value that has been revised by using additional information that's later obtained. So let's say P of C equals 0.01, which is the probability that we randomly selected subject has cancer. That was given to us. So P of C is an example of prior probability, right? So we use that to determine the other probability. So use the additional information that the subject has received a positive test result. We find that P of C with respect to positive test result is 0.0748. And that is a posterior probability because it uses that additional information of the positive test result, all right?